And we are live. Okay, so welcome to Math with Doug. It is Geometry with Doug. We are starting a new unit about geometry, so it's going to be a lot of the basics today. The dog is exhausted because she went and had a sleepover somewhere else last night. And I think in this other house she was spoiled rotten and brought for many walks, and she seems very tired. She's ready for a nap. Okay, so lie down. Stay. That's her job. And it is springtime. It is really nice, mild weather outside. There is snow melting off of our roof and drip, drip, drip everywhere. I'm enjoying it. I was outside wearing just a t-shirt before, and maybe I shouldn't be. I should have been wearing a jacket, but I just couldn't help myself because the weather is so nice. And it means I can get outdoors and do all sorts of fun stuff that I have been waiting for weeks to do. And I am not wearing a sports jersey, just a regular t-shirt. Although this regular t-shirt probably has sawdust on all over it, and it will have chalk dust on it soon, because let's get into some geometry. Ooh, what's that? It seems that there's already something on my chalkboard wall besides the heading of this unit, and that is a point. Let's call it point A. I like to give my points names. So a point is a single location. We draw a dot to show it in geometry. And it is a building block that we use when we are drawing some more complicated shapes. I'll put it that way. So, okay, the point. We know what the point is. What's the next thing? Let's talk about a line. I'm going to draw a line. I'm going to draw the line so that it goes through point A. And a line goes forever in both directions, but of course you can't draw forever in both directions. So when you draw a line, you're drawing part of a line. And yet no one's going to argue with you if you say, I just drew a line. I can put another point on this line, and I can give it a name as well. I'll call this one B. And I can denote a line by giving it a name. By putting 2 points on the line, it helps me to give a name to the line. I can say this is line AB. And then the notation we would use for that is we draw a line across the top of the letters, and we put arrows on both ends. And then people can see, okay, this is a line called AB. It has point A and point B on it. It all makes sense. So this end of the line continues onwards, and we know it can go on forever, but we can only draw it so far. This end also goes on forever. What about a line segment? Let me draw another one. This time I'll draw down here. And of course the direction of the line doesn't really matter. I could have drawn this line so it went straight up and down. I could point it any which way. So long as it obeys the rules of being a line, it's okay. So let me choose slightly different direction and draw another one. But this time I want to refer to it as a line segment. I'm going to put points on both ends, and I'm going to call them C and D. So this is line segment CD, and I could refer to it like this. Notice how I didn't put the arrows on the 2 ends. What will happen very often is, you can see even in math books, this, and it is referring to a line, and isn't necessarily meant to be a line segment. The line segment is like the line, except it ends at these 2 endpoints. Of course, we know that if we wanted, we could draw the line further, and we could say, okay, line segment CD is part of this line, which I can also call CD. So we get used to this notation. It helps us to explain something without having to write a whole paragraph. Line segment CD, line AB, that is efficient. So sometimes when you have a line, you won't bother putting the 2 arrows on the ends, and that's okay. And then the next one I want to draw is a ray. I have to find a spot to put it. I think I'm going to put a point here. I'm going to call that E. Of course, I can use any letter I want. I don't have to present things in alphabetical order. And then if I draw from that point, and then I put an arrow on the end, and put another point on it, which I'm going to call F, I have drawn ray EF, so that is a ray. So this is a line. Here we have a line segment. Often referred to as a segment for short. And then we have this, which is a ray. A ray is kind of in between a line and a line segment. It has one endpoint, and then it goes on forever in the other direction. And if we want to show that, then we put an arrow to show that this is a ray. And then we have some symbols that we use for that as well. We would refer to ray EF like this, with an arrow just on one end above the letters. Okay, I've covered quite a few things. Let me put little check marks. I have a list over there that you can't see, but I'm going to put little check marks next to the things I've done. So we have point, we have line, we have segment, we have ray. That's it so far, but it's a pretty good start. Let me see how I'm doing for time. I have such a long list, and some of the things I want to spend a little bit more time on than others. But we're getting going. We're getting used to the terminology, the words that go with the study of geometry, because if we don't do that in the first lesson, then as we move on to subsequent weeks, we might find the teacher is talking about things and mentioning things like lines and rays and points, and the student isn't sure, wait, what are we talking about? That's why we have to start off with some terminology in our most basic lesson. Pretty good. I'm going to erase though. What do I want to do next? I'm going to try drawing two rays that go into two different directions, but that have the same endpoint. Yes. So, getting my eraser cloth, get all of this erased, and get my ruler. So I'm going to put a point here, and I'm going to draw a ray going away from that point in this direction, and I think I will label the point. I guess I'll use A. I like using A for points. And then I'm going to put another point on the ray and call it B, so that now we can see I have drawn ray AB, and we can talk about it later and not get it mixed up with any other rays that might happen, like right now. Okay, if I draw another line and put an arrow on the end to show that it is also a ray coming from that point A, and I guess I'm going to call this, you thought I was going to use C, but I decided I wanted to use D. Okay, so we have ray AB and we have ray AD. We can refer to this point A now, besides being point A, we can also refer to it as a vertex. Vertex A. A vertex is a point that has more than one line or line segment coming out of it. And when you arrange things like this so that we have vertex A on these two rays, we also have created an angle. Let me check off a couple more things on my list. Vertex and angle. So this is an angle. We have an angle. I'm going to measure this angle. I like to show this. The angle symbol looks like that. And then we can call it angle A. A lot of people would want to call this angle A. But that is one way of dealing with it. But it can be confusing because sometimes in a drawing you have a lot of stuff going on, and you could say there's more than one angle A, and the student would say, wait, which angle A? I see more than one angle A there. So to be really clear, what I prefer is the three-letter method for naming an angle. So I'm going to call this angle BAD. Not because it's bad, that's just a coincidence because of which letters I use. I arranged the letters though so that the vertex of the angle that I'm talking about, that I want to draw students' attention to, is the middle letter. So BAD describes this angle, and then you don't get it mixed up with any other angles that might have A as a vertex or might also be in your drawing. But you might say, wait, why does he have to start with the B? What if he started with the D? What if you wanted to call this angle DAB? That's okay. So this angle can be referred to as angle DAD or angle DAB. So long as we are careful which letter is in the middle, then it makes it clear which angle we're talking about to the person who is reading what we're writing or who we are showing our geometry to. Now we are going to try measuring this angle, whatever it's called. I'll just call it angle BAD. So I'll erase this. And how do we measure an angle? We measure an angle with one of these things here, and this is a protractor. Protractor. So I'm going to add the word angle onto my chalkboard wall, but I'm also going to add the word protractor. Now, this is not exactly the same as protractors students usually use, but it is very similar. There are all sorts of protractors. I have another one here. This one's made of wood, this one's made of plastic, but both of these are designed to be used with chalkboards, which is why it's so big. And they're both pretty much the same in every other way. How you use them is the same. I also have this thing, which is a whole circle, but it's also a protractor, and it can be used for a lot of the same purposes. Although I really like this for tracing when I want to draw circles. The protractor that you might have, that you might buy in a geometry set, besides being smaller than this one because it's not designed to be used with a chalkboard, is often going to be transparent, and that's useful because if you can see your drawing through the tools you're using, it makes it easier to do drawings, to measure things, to draw new things, and to see what you're doing and not make a mess. How does this thing work? Okay, you have to mention that it has this dot on the bottom. Now the dot, sometimes there would be more wood and there would be a hole there. This one has the dot right at the bottom edge. And that dot is to help you place the protractor correctly so that that dot is on a vertex, the vertex of the angle that you want to measure. What else does it have? It has a baseline. A baseline, in this case, is just the bottom edge of the protractor. And it's straight, and it's used to help you find one of the lines that makes up your angle so that you can draw the angle or measure the angle. What it also has is these two sets of numbers. And why are there two sets of numbers? That can seem a little bit confusing, but they are there for a very good reason. We need the two sets of numbers because a protractor can be used in more than one way. You can measure this angle by putting the baseline along this ray AD. Or you can measure the same angle by putting the baseline along ray AB. And since you have to have two choices in how you do that, that is why you have to have the two sets of numbers, because which set of numbers you're using depends on whether you're reading on the left side or the right side of the protractor. Okay, let me measure this angle with this protractor. I'm going to measure it twice. I'm going to take both strategies that we can use. Okay, Moko, get off of your chair. Get up. Lie down. Stay. Stay. Okay, I'm going to measure using both strategies. So first, I'm going to get my 0 dot. I like to call this the 0 dot. I don't think that's an official name. Put the 0 dot on vertex A and make sure the baseline goes along ray AD. And now I want to measure, okay, how wide is this angle? What I'm going to do is I'm going to use these numbers. I need to count up from 0. So I look at the two sets of numbers and I realize that the inside set of numbers over here on the right side of my protractor starts from 0 and then climbs up higher. That's the set I need to use. The other set of numbers on the outside starts at 180 and gets smaller, 180, 170, 160, 150. So I always want to count my angle, the size of my angle, by counting up from 0. So I'm using the inside set of numbers. And if I do that, I go up to where I see this other ray that makes up the other arm of my angle. And I realize that's happening between 50 and 60, but quite close to 60. It's about 58 or 59. And that is accurate enough for me to label my angle as 58 degrees. Now, another person could walk up and measure and they could get a measurement that's slightly different. It's just, that's what we call measurement error. And it's not really an error, it's not a problem. So if you had measured the same angle and you got 60 degrees or 59 or 61, then you're close and you are doing what you wanted to. You are fulfilling the purpose of your exercise. Now, what if I decide I want to measure the same angle, but I don't want to use ray AD as my along the baseline of protractor. Instead, I want to use ray AB. Notice how I'm holding the protractor upside down. I still want that 0 dot to be on vertex A. And then I make sure the baseline goes along this time along rate AB. And what I see is there's those two sets of numbers again, but this time I find myself having to use the outer set of the numbers. The outer set of numbers because I want to count up from 0. And over here on this side of the protractor, the outer set of numbers are the ones that count up from 0. So counting up from 0, I follow the numbers and I realize I have an angle that is between 50 and 60 degrees, but very close to 60. Because it's the same angle, we're not surprised. So I would still get the same measurement. I'm still saying that that is a 58-degree angle. I can measure angles with the protractor. It helps to know what the word protractor means if you need to do that. I can also draw angles with the protractor, and that's another thing that we will get into. It works in a very similar way. You have two sets of numbers on the protractor because when you're measuring or when you're drawing, you have choices about which side of the protractor you want to use, and therefore you have a set of numbers that will work for you regardless of which approach you use. Now, I did mention the measurement was 58 degrees, but I forgot to talk about, well, what is a degree? A degree is the unit measure for an angle. We can't use things like inches and centimeters the way we do when we measure other things because of the nature of the angle. This, for instance, if I took a ruler and I wanted to measure how far apart are these 2 points, I could certainly measure that, and in inches it looks like about 4.5 inches. But why would I choose those 2 points? Why would I not, for instance, say, okay, well, how far apart are point B and point D? And I'm getting a very different answer of 13 inches. So you can see how this tool isn't right for measuring the angle, because the way the angle is, the two lines are very close together, close to the vertex. But then those two lines get much further apart when you're further away from the vertex. We need a different tool. We use the protractor, and we call the unit of measure, the smallest bit of an angle that we use, we call that the degree. So finally I'm able to check off the word degree on my list here. And the word protractor, I have not checked that off yet. I'm doing well. How am I doing for time? I'm doing well. Okay. I want to spend a little bit more time with angles though. So, measuring angles with the protractor, drawing angles with the protractor. I think first I'm going to try measuring a couple more. So we measured this one. Now, without knowing how big the angles are, I'm going to create some angles and I'm going to do them quickly with the ruler, and then we're going to try measuring them so that we can practice using our protractor. So I'll erase this. And I'm not going to label points on these angles. I'm just going to draw some angles simply by taking a straight line and then another straight line. And making sure those two straight lines meet at a point. We have a vertex, even though I didn't put a point there and make it obvious or give it a name, we have a vertex, there's our vertex. But that's one angle. Let's draw another one. This one is quite wide. It's going to have a bigger degree measurement than angle BAD that we just measured. This one is going to be bigger than 58 degrees. But exactly what is its measure? I don't know yet. I have to get my protractor to find that out. I'm going to draw another one, and I'm going to deliberately make this one more of a skinny angle. So, how about if I do this carefully? So this is going to be less than 58 degrees. Notice how this one's sort of pointing in the opposite direction. And it doesn't matter. We're able to measure an angle no matter which way the angle is pointing. Okay, let's get the protractor and practice this bit. If I'm in the habit of wanting the curved part of my protractor to be up on top instead of holding it upside down, there's no such thing really as upside down with the protractor. But if I'm in the habit that I like this curved part on the top, then I'm going to be tempted to walk over to this angle and place the protractor like this, so that the 0 dot is on the vertex of my angle, and the baseline is here on this lower arm of the angle. And then I am counting up from 0, so I'm using the inner set of numbers. And when I go up here, it's looking to me very close to 80. Maybe it's 81 degrees. I think I'm going to say that that is 81 degrees. Someone else might like holding their protractor like this. And they might walk over to this and think, you know, I am going to set the 0 dot against the vertex like this. I am going to set the baseline on this arm of the protractor, and that means I need to use the outer set of numbers. Counting up from 0, I'm getting the same measurement, 80 or 81 degrees. I'll just leave that there. So, how about this one? Now, I'm walking towards it, but I find myself, instead of using, like here I'm back to putting the roundy part on the top, instead of using the right side of the protractor like I did with this one, I find myself needing to use the left side of the protractor. Well, this is why protractors are designed the way they are, so that I can do that, so that I have the freedom to approach any angle and measure it in a way that's convenient. So I'm going to put the 0 dot of the protractor on the vertex, and I'm going to arrange for the baseline of the protractor to go along this lower arm of the angle. And counting up from 0 to get my degree measure, I have to use the outer set of numbers. I'm over here on the left side of the protractor, so I'm using the outer set of numbers. And when I count that, it looks to me like I would call this 22 degrees. So this angle is 22 degrees. And this little circle up high, a superscript, is how we, it's the symbol we use to show degree measurements, so that people who are reading their geometry will see that and realize, oh, okay, that's a degree measure. I know because I see the little degree symbol. If I want to walk up to this one, this angle with my protractor held like this, I can still measure it. I get my 0 dot on the vertex, I get my baseline going along this time the upper arm of the angle, and counting up from 0, which means I'm using the inner set of numbers this time, I am getting the exact same measure of 22 degrees. Very flexible tool. The two sets of numbers are there for a good reason, and all you have to do is practice using it for a while, and you get used to that and you start to appreciate it. I appreciate it. Next thing I'm going to do is use the protractor to draw some angles. You notice how when I drew these angles, I just used a ruler and I just placed lines anywhere I wanted. But I didn't know exactly what size angle I was going to get. I didn't know what size angle I had drawn until I took the protractor and measured it. Now I'm going to draw a couple more angles, but this time I'm going to use the protractor and I'm going to choose how big an angle I want to draw first, and then make sure I get one that is exactly that size by using the protractor. And before doing that, I am going to take a sip of my fizzy water. This time we have lime. Okay, that's good. Erasing these two angles. Let's draw two more. And because students probably would enjoy it, I'm going to not only draw these, I'm going to name them. So I'm going to put some points in the drawings, and I'm going to label the points with letters, and then I am going to name the angles that I draw. I'm going to do it all. So the first thing I need to do now, I really want to grab the protractor and start using it. But the thing is, to draw an angle with the protractor, you need a line to start with, or a line segment. So I'm going to use a ruler to draw a line segment. And of course, yes, you can use the flat edge of a protractor sometimes to draw a line, and it is useful in that way sometimes. Okay, let me draw two. This time, over here, I'm going to draw an angle that opens this way, so I'm going to put its lower side like this. Okay, that's pretty good. It got a little crooked at the end. This one, I'm going to have it opening that way, so I'm going to draw its lower side, make the ruler more steep. There. Now I want to put this away, and I want to use my protractor. So really, when you draw a line, or a line segment like this, you always have a choice. I could draw my angle so that this is the vertex, or I could draw it so that that is the vertex. It's really up to me. I'm choosing to use this as my vertex. And in fact, I'm even going to put a point there and label it, and I will call it A. Now, let's say I want to draw an angle that is 64 degrees. I'm taking the 0 dot of the protractor and I'm putting it on my vertex. I am taking the baseline of the protractor and I'm putting it on the line that I drew. And because I want to count up to 64 degrees, I want to count up from 0. That means because I'm over here on the left side of the protractor, I am using the outside set of numbers. 0 up to 64 means that I could put a little mark here, right where 64 is, And at that point I can use any straight edge, the edge of the protractor or a ruler, and I can connect my vertex A with that point that I just made. And in fact, I'm going to label that point, let me see, F. And over here I think I'm going to put a point, and I'm going to call this R, point R. So we can see that I am having fun with little three-letter words that I can make when I name angles, and I am going to call this angle FAR. It's a little messy. There. Angle FAR, angle FAR. Isn't that cute? Okay. And how big is this angle going to be? This time we don't have to wonder. We don't have to measure it to find out how big it is. We know. We chose to make a 64-degree angle. This should be 64 degrees. So I'm going to put this little arc into the middle of the angle to show that I am labeling this angle as having a measure of 64 degrees. But then, of course, I can also double check. I can walk up to that angle with my protractor, and using either of the strategies for measuring an angle, I can set up my 0 dot and my baseline, and then I can use the appropriate set of numbers. In this case, it's the inside set, and I see that yes, that has done quite a good job of being a 64-degree angle. Any slight difference between the angle I wanted to draw and the measurement I get is called measurement error or drawing error. Maybe I made a tiny little bit of mistake when I was drawing it. Maybe the mistake happened when I was measuring it. So long as we end up with a degree measurement that's really close to what we intended, we're doing it right. Okay, let's do this one now. I want this one to open that way, and I want it to be a bigger angle. Notice how these go past that big number 90, but they keep going. And it's because we can draw an angle that's bigger than 90 degrees. 90-degree angle is something that we want to talk about. But I'm not going to do a 90-degree angle yet. Maybe I'll draw one right after. What I'm going to do is I'm going to label this point, and I think I'm going to call it E. And then, I think I will put a point over here and call it point P. And now I am going to draw an angle. How big do I want it to be? I want to show that I can draw an angle that's bigger than 90 degrees, so I think I'm going to try to draw a 110-degree angle. Using angle E as my vertex, I'm getting the 0 dot of the protractor on vertex E. I'm making sure the baseline goes along the line I drew, and then counting up from 0, which means using the right side of the protractor, I'm using the inside set of numbers. I count up to 110, and I make a mark. And then I can take any straight edge. I'm using the protractor's edge this time. Draw through that mark. I put a dot over here, and I'm calling that point T. I can put a little arc here, but I need to give it its measurement. And what was its measurement? We intended it to be 110 degrees. I'm feeling confident that it is 110 degrees. I use my degree symbol, and we see angle PET, angle PET. The dog. Angle PET is 110 degrees, and then we can double check by taking our protractor, setting up our 0 dot and our baseline, choosing the appropriate set of numbers, counting up from 0 and saying, yes, this is a 110-degree angle. We have succeeded. I left some space in the middle, so I think it's time for me to introduce the right angle. Right angle. Right angle. The right angle is a 90-degree angle. I am going to label this angle PET. Okay, a right angle is a 90-degree angle. So I want to draw one that's exactly 90 degrees, and then we're going to talk about it a little bit. Okay, I will start by, I think I'll put the line like this. I don't want to try to make the lines always point in the same directions, because it starts to sound like you have to do that. You can put a line anywhere we want. If we want to draw a right angle, I can place the line anywhere I want, and then make sure that I have a right angle, meaning a 90-degree angle, using the same techniques that we were using with the last couple of angles. So I'm going to call this vertex I, and I am going to approach it with my protractor. I am holding my protractor this way, but if I wanted to, I could hold it this way. I'm holding my protractor this way, putting the 0 dot on vertex I, making sure the baseline goes along the line I drew, counting up from 0, which means the outside set of numbers, until I get to 90. And then I put a mark, I draw a line with a straight edge through that mark to vertex I, and I have a 90-degree angle. And of course I could label that the usual way with an arc and 90 degrees using the degree symbol. But what I could also do is label it with a little square. More chalk, please. So I can put this little square into the corner, and that is another way of saying this is a 90-degree angle. Right angle, 90-degree angle. Right angle, which is a 90-degree angle. And let's see, I can call this point J, and this over here I'll put point G, and I have angle jig. My angle jig, or my angle gidge if I want, is a 90-degree angle, and we see all the different ways that we can show that. Now, a right angle is a special angle that we use in a lot of applications. You know, for instance, that usually most of the pieces of paper that students work with have this shape. They have a 90-degree angle as their corner. It's a convenient shape for paper. Well, this piece of paper is a rectangle. And that's just one example. You can look around you anywhere you are and you see, I'm looking at windowsills and window panes. I see a set of shelves. I see the edge of a table. There's a refrigerator over there. There are all these things, and I see all sorts of 90-degree angles, all sorts of right angles. They are very useful when we are building things. They're very stable. They look nice. So there are reasons that we want to use them. This thing here, this is a carpenter's set square, which I use in my woodworking. And it's designed so that this corner is a 90-degree angle. And you might think it looks a little bit familiar because if you have a geometry set where you got your, which might include your protractor, compass, a ruler, some very useful tools, you might have one of these. Now notice how this one, it has a 90-degree angle on this corner. It has two 45-degree angles, also very useful size for an angle. And there might be another set square in your geometry set that has the 90-degree angle, but it also has a 30-degree and a 60, so it's a little bit longer and skinnier than this one. This is used very conveniently with wood because, for instance, when I want to cut a piece of wood, I might want to cut it so that all of the sides are square. In fact, I wanted this piece of wood to be square, that this side of it would be a square. And that means it's going to have square angles. So I can set this thing up so that there's sort of an edge here that lies along the one side of the piece of wood. And then you can see that this side is going very nicely along where the adjacent side has been cut. I can turn this around, do the same thing over here. And what I'm doing is I am checking if the angles on the corners of this block of wood are square, if they are 90-degree angles. That's convenient. So we are talking about this. Now we're talking about a shape, a square. Yes, the square. So we want a square piece of wood. I wanted a square piece of wood. We may as well talk about a square. What is a square? Let's see here. I'm checking off right, the right angle. Checking off some measuring angles and drawing angles. Covered quite a lot of the topics, and it's a good thing because I've used quite a bit of time. Okay, I'm going to erase these, and I'm going to play around with that square piece of wood, and we'll talk a little bit more about some of the same concepts and some new concepts. So erase, erase, erase. I talked about how I like this round protractor. Partly because it allows me to make circles easily, like when I'm teaching fractions and I want to draw circles and call them pizzas. being able to trace around it. Well, of course, that's not the only shape that's convenient to trace. I can trace this shape because I know it's a square because I cut it to be a square. So when I place it on the wall and then just carefully trace around the outside of it, trying not to get too messy, what I am doing is I am drawing a square. Pretty good. I drew a square. What's a square? A square is a four-sided figure that has the four sides are the same length as each other, and the inside angles are right angles. They are square angles. They are 90-degree angles. And now that I've drawn that, I can sort of check it by using my protractor. So if I bring my protractor and say this, I'm going to call this a vertex. I won't label these with letters. I'll just put dots. I'll put points to use as the vertices. The four vertices, vertices is plural for vertex, the four vertices, the four corners of a square are each vertices. Well, I should be able to measure all four of these angles and they should all be 90 degrees. So I set up my 0 dot and my baseline and I see, yes, this nicely is looking like 90 degrees. How about this one? 0 dot baseline, 90 degrees. Yes, looking good. 0 dot baseline, 90 degrees. 0 dot baseline, 90 degrees. This is good practice in using my protractor. What else could I do? I can mention that these two sides, and now I think I should give these names. So I'm going to call this square ABCD. Side AB, which I can denote with line segment AB, because basically that's what it is, has to be parallel to side CD, line segment CD. If it's really a square, and we're feeling quite confident that it is, side AB should be parallel to side CD. And what does parallel mean? It's kind of like when you see train tracks, the two lines that never will cross because they always stay the same distance apart. It's kind of like tracing on either side of your ruler. You have made a pair of parallel lines. Is this the only ruler that works to do this? No. I can use this ruler and trace on either side and I have parallel lines. There are other ways that we can do this. I know, because I feel confident that the corners of my calculator are square, right angles, I can trace this side, and I have another set of parallel lines. They don't have to be the same distance apart as another set of parallel lines. These ones happen to be a bit more than an inch apart, so do these, but these are about 3 inches apart. That doesn't matter. The thing that matters is the two lines, if they're 1 inch apart here, they stay 1 inch apart no matter where you go along the length of the lines. So the distance that the two lines are apart remains the same. And that applies perfectly well to side AB and side CD of this square. However far apart those two sides are, they're staying the same distance apart over on this side of the square as they are over on that side of the square. Interesting. Shall we measure them? How long is the side length of this square? I haven't actually measured it. So let me measure it now. If I measure side BC, I am saying that is just about exactly 6.5 inches. If I measure side AD, I am seeing the same thing, 6.5 inches. So I have more evidence that AB and CD are parallel lines, parallel line segments. But it's not just AB and CD, it's also BC and AD. BC is parallel to AD. Here's a way of saying that. We can use this symbol that means is parallel to. And interesting, a square has two sets of parallel lines. This set here that are looking sort of horizontal, and then this set here that are looking sort of vertical in my drawing. Two sets of parallel lines. And all four of the internal angles, I'm losing my little clip there off my chalk folder, all four of the internal angles are square angles, or 90 degree or right angles. A lot of stuff there. A square seems like such a simple thing, and you think, oh, you can't really talk about a square for very long. There's not much to it. But actually, there is quite a lot to it. It uses the idea of parallel lines. It teaches us about parallel lines. It uses 90-degree angles. It teaches us about 90-degree angles. It's kind of an interesting shape. Square angle, I've got that. Parallel, I've got that. And there's another thing that this, I'm glad I didn't erase it yet. There's another thing that this these 4 90-degree angles are helping us to learn, which is the idea of perpendicular. Perpendicular. It's long. Perpendicular. Perpendicular lines are lines that form a 90-degree angle. Square angle, right angle. So when you find a right angle, you have found a pair of perpendicular lines. Once I realize that this angle here, I'm going to erase some of this stuff. Give myself a bit of room. I'll erase all these parallel lines. I'll erase this little statement here. Angle ADC. So I'm talking about this angle right now. Angle ADC it has a measure of 90 degrees, or it is right, and thus, useful word, thus, line segment AD and line segment DC are perpendicular. Long word. Perpendicular. Okay, managed to get that. I wrote that word twice. Oh, uppercase, lowercase. All right, so the square has 2 sets of parallel lines. It has 4 sets of perpendicular lines. Yes, I would say it has 4 sets of perpendicular lines. It has right angles, it has square angles, it has 90-degree angles. The 4 sides are the same length. All 4 sides of this square should be 6.5 inches. We measured side AD and side BC, but if it really is a square, it means that if we measure side DC, we should also get 6.5 inches. Oh, and we do, that's nice, and side AB, of course. So it is a square, it is a very good square. I'm proud of it because we know that I traced it from this, and I actually had to try to cut this with the saw. It was a long board, I think. Yes, so these were the 2 outside faces of the long board, and I cut with my saw twice to cut a square piece of wood because I wanted to make a bowl. So I wanted that piece of wood to be square, and if I didn't cut it well, I would still be able to make a bowl with it, but I would end up wasting some of the wood. I would end up with more of the wood landing on the floor in the form of sawdust and shavings. And that I don't want to waste the wood. I want to get as many bowls out of a board that I can. So cutting nice square angles using my set square and my saw is very helpful. Okay, next thing I want to talk about. Okay, I'm going to check off perpendicular. I also have a few notes over on this side. Square's over on this side, so I'm going to check it off. Before I erase it, I think I want to talk about more things. Really, I can talk about just about everything that's left on my list, except for one other shape that we're going to talk about soon. I'll save that for last. So, one thing I can do is I can mention the idea of collinear. I'm going to put another point on this side's line segment BC that happens to be a side of my square, and I'm going to give it a letter. I kind of already went through my alphabetical order, so I'm just going to give it any letter that I want. How about Y? There, like the Y in geometry. Okay, so now I have 3 points on that side of the square. Those 3 points are collinear. I wanted to talk about that. So The thing is, why do I have to have 3 points to talk about collinear? It is worth mentioning. I'll draw a line, and I'll put 2 points on it. How about W and V? Are they collinear? Do I prove what collinear means when I only have 2 points? Not really, because the thing is, any 2 points, anywhere you put them, you can always draw a line through them. But only 3 points will only have the same line drawn through all 3 if the points really are collinear. It means they're all on the same line. So this line or line segment that I can call CB or BC has all 3 points B, Y, and C on it. Those 3 points are collinear. They are on the same line segment. They are on the same line. Here, we haven't really illustrated what collinear means unless we put another point on the line, and if it's on the same line as W and V, then all 3 of these points, W, S, and V, are collinear. So I wanted to mention the idea of collinear. I'll put the word collinear here. Will this fit? Yes, it will. There. Yes, it did fit. Okay. Now, so I've managed to talk about collinear. I'm glad. I wanted to get that in there. Now, perimeter. I think I'm starting to get quite a crowd of words and diagrams and symbols on my chalkboard wall. Perimeter. That's an important word. The perimeter is the measure outside the edge of a shape. The best example I always think of when I'm trying to explain that to students with real life examples is a fence. If you have a lot of land that is a square, for instance, and the side length of the square is 100 yards. If you needed to build a fence all the way around the outside edge of that square, because for instance you want to keep animals on that piece of land and you don't want the animals to be able to escape and get onto the road, then you would build a fence all the way around all 4 sides of your square. And that means you're building a fence on the perimeter of that shape, the perimeter of the square. So fences are a good way of remembering perimeter, because there are other concepts in geometry, and if we want students not to get things mixed up, it's good to know what perimeter means. It's the distance around the outside edge. So let me modify my drawing a little bit. Let's pretend that this is the piece of land that we're talking about. I didn't really have to erase the letters, so I'll put them back. So that was A, B, C, D. It's just that I didn't want that Y there. Okay, so if we are keeping some animals in there, and each of these sides of the square are 100 yards, well, I don't really have to label all 4, because I know this is a square. And as soon as you know one side length, well, then you know all 4, because they all have to be 100 yards if it's really a square. What's the perimeter of that? Well, what is the length of that fence? The length of the fence will be 100 plus 100 plus 100 plus 100, therefore will be 400 yards. That's one way of calculating it, just simply by adding together the lengths of the 4 sections of fence. But it's not the only way of figuring it out. I'm going to keep the word perimeter here and get rid of some of the other stuff. There. Now we have some room. That's one way of doing it, but we can also say that, let's say we want to make a formula for this. The perimeter of a square is equal to side length, which is S is what we use to give the side length of the square, plus S plus S plus S. Well, that's the formula I just used. Perimeter equals 100 plus 100 plus 100 plus 100, and it ends up being 400 yards. But another way that we can give the perimeter of the square is to say it is going to be 4S, because there are 4 sides of the square and they're all the same length. We can do that. We can say 4 times the side length. In this case, that is 4 times 100. And that is also going to give us 400 yards. we have shown two different ways of finding the perimeter of a square. Interesting. I can check off perimeter. Now, I left this square here for so long partly because I also want to talk about congruent. The word congruent, where will I put that? I'm going to put it here. Congruent means equal. It means that when you have two shapes, that they are the same size and the same shape. So you can't say a triangle is congruent to a square. They're not the same shape. You can't say a little tiny square where are my dice? Where are my dice? Here. I want to talk about tiny dice. This is a really small dice. Makes me look like a giant, doesn't it? So a little square is not congruent to this big square. They're not the same size. They are the same shape, but they're not the same size. So that's what congruent means. Same size, same shape. Same size, same shape. There. Now I'll erase my perimeter. I want to make another square that's the same size and the same shape. In fact, I want to make three, a total of three. We already have one. So we have square ABCD, and I want to make two more squares, and I want all three of the squares to be congruent. So I want to talk about two different approaches I can use to do that. I'll erase my perimeter calculations. I'll erase this 100-yard thing because that was in our example of the field the animals would live in. But it is not in the example that we're doing right now. So what can I do? How can I do this? One way of doing it is to draw a line segment that is 6.5 inches long. Remember, we had measured this before. These four side lengths were 6.5 inches. I can draw a line segment that is 6.5 inches. Do I have to draw up and down or left, right? Not really. If I want shapes, congruent shapes do not have to be pointing in the same direction. So I'm going to illustrate that. I'm going to draw a 6.5 inch line segment. And then I am going to get my protractor and I am going to use the 0 dot. That's not how I do it. I put the 0 dot on one of the vertices. And I make sure my baseline goes along. And now this is kind of getting in the way, but on this line where I see 90, I could put a mark here, I'll put a mark there. And now I'm going to use those marks to draw a second line segment, which has to be perpendicular because I just drew a 90-degree angle. And I'm going to make sure this second line segment is also 6.5 inches long. I'm not finished, I have to keep going, I have to do it again. I think I'll use this vertex this time. I am going to set up my 0 dot and my baseline. I'm going to mark over here. Yeah, I guess I would use my straight edge, except no, I need it to be 6.5 inches long. So I'm not just going to use any straight edge, I'm going to use my ruler. 6.5 inch line that goes through that vertex and through those marks. There. The last one I can just draw with the ruler. Just try and connect these two vertices. And then I can also measure it and make sure that it's 6.5 inches. And it is. I have managed to make a second square which is congruent to the first one. Let's call it E, F, G, H. I guess I should put points there so that we can see that it's the points that I'm labeling as E, F, G, and H. I have drawn two congruent squares. They are the same size, they are the same shape because they're both squares. They are the same size. We made sure as we drew them. I can put the little square symbols. I can also put an arc and right 90 degrees if I prefer to do that. So I'll do a mixture of those. That's fun. Okay, and I said I was going to do one more. I want three because I want to use a different strategy. I think some students may have predicted that it might have been easier all along for me to just keep on using this. If I trace around if I drop my chalk on the floor, I'll reach and get another piece of chalk. Let's get back to doing this correctly. Trace around the outside edge. Move my It's actually, maybe it was easier to use the protractor. Okay, let me just make sure that I put this back into its position well. Pretty good. Okay, I have drawn a third square which has to be congruent to the other two. I traced the same block of wood that I used to make the first square. I am going to call this E, F, G, H, I, J. What is it with this alphabetical order? K. Do I have to have them in alphabetical order? Not really. So I'm going to put an M here. There. I, J, K, M is the name of my third square. These three squares are congruent. They are the same shape because they are all squares. They are the same size because they all have side lengths of 6.5 centimeters. Of course, they all have 90-degree internal angles because they wouldn't be squares if they didn't. That's pretty good. So I've covered the concept of congruent. I've covered everything. I have very little time left. I am going to pick up the chalk holder that I dropped. And I have two more things on my list. So I'm going to start working on those and we'll see if I have time to complete them. That was fun though. I'm glad I decided to do that. I'm glad I brought in that block of wood and this incredibly useful tool that only costs around $5. Incredibly useful. I have 3 of them. That way, when you're saying, where's my set square? And then you put it down somewhere, you just grab another one. That's why I like having more than one set square. Okay, so I want to talk about the rectangle. Now we're not getting into all of the shapes. We're not getting into all of the, even all the simplest shapes. We haven't done anything with circles in this lesson. And I mentioned triangles once, but we haven't been using triangles. But the square and the rectangle, I think these both belong in a first lesson of geometry. Because the rectangle, it has a lot in common with the square. We've actually covered an awful lot of the terminology and the techniques that we use when we work with rectangles. Because we made the square. Is a square a rectangle? Is a rectangle a square? That sounds like it's a really simple question, but it actually can become a complicated question when you think about the definitions of these. But a square is a rectangle. But a rectangle does not have to be a square. That's my answer to that question. Because the thing is, rectangles have a little bit more flexibility than a square. A rectangle, not all 4 sides have to be the same length. A rectangle does have to have 2 sets of parallel sides. Let's start drawing one. 2 sets of parallel sides. Okay, so what I'll do, and those 2 pairs of parallel sides are equal in length to each other in a rectangle. What I'll do is I'm going to draw a line segment that is 10 inches in length. And then, what I'll do, a bit of a cheat I guess, is I will place this here and give myself a start of drawing another line segment which is going to be, it is going to be parallel. That has to be parallel because I traced that block of wood and we already sort of proved that the opposite sides of that are parallel. Now, in order for this to be perfect, I have to know where to start and where to end this line. But it definitely has to be made longer so that it's as long as this line. So what I'm going to do is I'm going to deliberately make it longer than this line that I started with. That one's 10 inches. This is longer than 10 inches. What do I do now? What I will do now is I will get my protractor and I will set myself up using this vertex, 0 dot baseline, and then I will make a mark at 90 degrees, and then using a straight edge, so I can see which little bit of the longer line I don't really need. I can even go and erase it now. I want to do the same thing over here. I'm going to set up my 0 dot and my baseline, and I'm going to make a mark 90 degrees, and then use a straight edge, And then I can erase a little bit of extra line that I don't need anymore. And what I just did, because I used the protractor, I know both of these are right angles. But I also know both of these are right angles, and I didn't use the protractor to draw those. That's interesting. Why do I know that these have to be right angles? Because I made sure that this line was parallel to this one. It's kind of interesting. But I can also double check. I can measure these and say, oh yes, that's a nice 90-degree angle. I can measure that, yes, it's a nice 90-degree angle. I'm feeling quite confident that I have a rectangle. These two lines are parallel. These two lines have to also be parallel, and we can check. All four internal angles have to be 90. It's really all the same thing as the square, except in the square, all four lines have to be the same length. In the rectangle, these two lines have to be the same length as each other, and we can show that by putting a little line through them like that. And then these two other lines, which we know are 10 inches long, have to be the same length as each other, and we can put little double lines through those. Starting to be a nice little diagram. How long? Well, we used that block of wood to trace, so I could presume that this line should be 6.5 inches long. So I'm not going to be surprised to measure it and see that it is, yes, 6.5 inches long. Yes. And then, are they the same distance apart? Well, of course they should be. So 6.5 inches, yes. 6.5 inches, yes. We have created a rectangle. This is a rectangle. Now, in a beginner's lesson, I'm not going to test students on giving the definition of a rectangle necessarily, or proving that something is a rectangle, but I am going to want the students to be able to talk about the parallel lines, the 90-degree angles, and of course the idea of perimeter. Oh, we may as well bring that in. I'm running out of time. Okay, we have a perimeter. I will do the perimeter as the last thing that I am going to talk about in this week's lesson. The perimeter of this one, because I measured and I was careful, the perimeter is going to be 10 inches plus 6.5 inches plus 10 inches plus 6.5 inches. Not exactly the same as it is with the square, where all of them would be the same. But 10 plus 6.5 is 16.5 plus another 16.5 is going to be 33 inches. That is my perimeter of this rectangle. The perimeter formula, not quite the same. The perimeter formula is going to be 2 times the length plus the width, which is really what we did. Length plus width, 2 times. So this formula also works for the perimeter of a rectangle. And with that, I think I have come to the end of this week's lesson. And this poor little dog is looking for her supper. Exhausted as she is not too tired to eat, ever. So, from Mocha, from me, from my very dusty, chalk dusty t-shirt, and from the beautiful melty weather outside, I am going to say thank you for being here. I enjoyed teaching you geometry, and I'm looking forward to teaching you more geometry next week. Bye-bye.